Okay, Assalamualaikum warahmatullahi wabarakatuh. So we continue with lecture number 4 for chapter number 2. Okay, again is a revision of organic chemistry. So we will see the interaction between the atom. Okay, the weaker intraatomic interaction between the atom. Okay, so intraatomic. So we also have inter and interatomic. So we see here for interatomic. So the chemical bond. So are the major force holding atom together within the molecule, and classified according to their energy level or how the bond are made. Okay, for example, the Lennard-Jones potential, dipole-dipole moment, van der Waals. Okay, so we have that classification, and the chemical bond have as the previous lecture, specific interatomic distance, bond length, and maintain also the specific angle relative to each other. Okay, so it will not be in any angle, but a specific angle. And in macromolecule, the collective contribution from a large number of bonds with small energy become very important. Okay, so interaction. This is just like our community. Okay, so when each other has a relation, so it will be much stronger. Okay, so these are the bond or interaction. So we have the first one is ionic interaction. Next is the covalent bond, free radical, and also the van der Waals bond. Okay, so first we see the ionic interaction. So ionic bonding involves ion of opposite charge, plus and minus, that form a bond state as a result of a Coulomb attraction force. Okay, so these are just from our EM1 or EM2. So you see this Coulomb force. Okay, so these are the attraction. Okay, these repulsive, and these are attractive. Okay, so plus plus repulsive, plus minus attractive. Okay, so if two charges of Q1 and Q are separated by a distance r, and in area of space with dialectic constant var epsilon, the force F between them is equal to this equation, the Coulomb attraction force. So these are the example. The binding energy of for natrium and fluorine. Okay, Cl. Okay, so we have this. Okay, so these are attractive, and these are repulsive, and this one is the best position for each Na plus and Cl negative. Okay, so these are the distance between these two atoms, Na plus and Cl. Okay, so 0.2 nanometer. So the total energy has a minimum value of minus 4.2 electron volt. Okay, so here this 4.2 volt. So these are the free Gibbs energy, the best free Gibbs energy for this interaction. Okay, so next we see the covalent bond. Okay, so covalent bond arise in a pair of neutral atoms such as 2H or 2C atom. Interaction is electromagnetic. Okay, electron from a charge separation between the nucleus and its electronic cloud. Okay, so the electron again. The two atoms share some electrons such that the energy and average separation between their nuclei are reduced. Okay, so this one sharing some electron. So the example of atom for electropositive: lithium, natrium, calcium, rubidium, beryllium, magnesium and calcium. Oxygen, electronegative, oxygen, selenium, sulfur, selenium, fluorine, chlorine, bromine, and iodine. Okay, so when a covalent bond is formed between two atoms of unequal electronegativity, so the electron pair or the electron cloud is directed more toward the atom possessing higher electronegativity. In the C-Cl bond, the pair of electrons in the covalent bond is closer to Cl than to C. Okay, electronegativity. Okay, because these are C, and this Cl. Okay, so the example here, sharing of electron, covalent bond. So C and oxygen, so sharing, this is a double bond, and here C and C sharing two electrons, so we have this double bond CH. Okay, and from our quantum mechanics, QM1 or QM2, okay, so we can see that the linear combination of atomic orbital LCAO, okay, these are from the first atom, and these are the wave from the second atom. Okay, so when they come together or near together, so the probability to do the linear combination is higher, and the probability of electron being at this point is much greater. Okay, so we have this one. So the next one is the free radical. Okay, so what free radical? So free radical is a species containing an odd number of electron. Okay, odd number of electron, and this is a highly reactive uh, species. Okay, so we don't want to have this free radical uh, moving around in our body, because it can sometimes can produce a cancer. Okay, so this during chemical reaction, so we have these two uh, type. When the covalent bond is cut, so the first one is homolytic. A bond can break in an asymmetrical way, so that one electron remains with each product fragment. Then we have heterolytic. A bond can break in an electronically unsymmetrical way, so that both bonding electrons remain with one product fragment, leaving the other with a vacant orbital. Okay, so here we can see that these are radical, and these are just a polar product. Okay, so these are homolytic, and these are heterolytic. So these are the free radical. Okay, so what we can say about this free radical is that the unpaired electron in the free radical possess a magnetic moment, and the radiation of microwave frequency induced transition between magnetic energy level of these particles. Okay, so what we can see here is that when it is have one electron, so we can rotate or do the rotation. So from this rotation, it produces the magnetic moment. Okay, and when we use the electron spin resonance equipment ESR, so we can study this magnetic energy level and the transition, so it can provide valuable information about the system or about the molecule. So what are the molecule, or what are the atom with that molecule? Okay, so from here we can know that whether that free radical is highly reactive or not. Okay, so if this free radical is highly reactive, then if it produced in our body, then it might produce a cancer at the point of infection. Okay, so the next one is the van der Waals bond. Okay, so the van der Waals force is interaction among neutral molecule, and energy is the range of 0.5 to 4.5 kilojoule per mole. So 100 times weaker than the covalent bond. So this must probability to be cut first before we cut the covalent bond. So 5 10 to 10 times weaker than the hydrogen bond. Okay, and then it can be classified as Hissem force. Okay, or in this van der Waals amount neutral molecule, so we can have dipole-dipole interaction, dipole induced interaction, or dispersion force. Okay, so here we have the Hissem force when they are due to two permanent dipole that are attractive and favorable arrangement along the axis joining the two molecules. These are dipole-dipole interaction. Thereby force between dipolar molecule that induce dipole moment of non-polar molecule leading to interaction between them. Okay, so these are dipole induced dipole interaction. London of dispersive force arising from induced dipole moment formation in non-polar molecule. Okay, so these are dispersion force. Okay, so these are the van der Waals. Okay, so the first one is the interaction energy for charge and dipole interaction. So these are the formula of the force. Okay, so when we see this figure, we can derive this equation. Okay, and for this figure, so we can derive that is these are the force or this interaction. Okay, and then the interaction energy for dipole-dipole interaction. Okay, so this one, first dipole, second dipole with a certain angle P and theta. Okay, so we are going to get this equation for the force, and here freely rotating, so these are fixed, these are freely rotating, so we are going to get this equation where these are the Hissem energy. Next is the interaction energy for dipole non-polar interaction, or dipole induced dipole interaction. Okay, so these are so we can get this equation or this equation. Okay, so we can derive from this figure this equation to this equation, and the interaction energy for two non-polar interaction. Okay, alpha and alpha. So if we put these together, so we are going to get this London dispersion energy, this equation. So we can produce this equation. So next is the Lennard-Jones potential. So if we put all this force, van der Waals, the free radical, the ionic interaction, the covalent bond. Okay, so we are going to arrive to this Lennard-Jones potential. Okay, so we can, when we put all together, simplify, so we are going to get this the Lennard-Jones potential formula. Okay, A minus A R6, the radius or the length, plus B R to the power of 12. Okay, so this one you can see from your chemistry, I believe. Okay, so these are the value for A, these are for the value for B, and these are for value for R for some type of bond. Okay, so we can see the electron potential for. Okay, so here these are the graph. Okay, you can see that again, same as before. Okay, so we have the attraction and repulsion, and these are the best position for these two atom to do the interaction. Okay, so this one. Okay, so next we have the hydrogen bond. Okay, so hydrogen bond is a special kind of dipole-dipole interaction that occur between a hydrogen that is attached to an oxygen, a nitrogen or a fluorine, or a lone pair, and a lone pair of oxygen, nitrogen, or fluorine in another molecule. So not as strong as OH covalent bond, but is stronger than the other dipole-dipole interaction, like you see previously. And the strongest hydrogen bond are linear. Okay, linear. The two electronegative atom and the hydrogen between them lie on a straight line. Okay, so here you can see that these are hydrogen bond, hydrogen bond, hydrogen bond, and hydrogen bond. So uh, stick together uh, two molecule into one. Okay, or attract two molecule into one position. Okay, so these are the length. Okay, the length of hydrogen bond depend on the next atom. So here these are nitrogen, these are oxygen, and O, oxygen, sulfur, and oxygen. So we can see oxygen and nitrogen 2.78, oxygen and oxygen 2.72, nitrogen and nitrogen 3.07, nitrogen and oxygen 2.93. Okay, so here we can see that 3.07 might be N, and N is doing the some repulsion. Okay, okay, so hydrogen bond helping the intermolecular bonding. Okay, so result in association of molecule and is affected by steric factor. Okay, so you can see here these are two uh, chain or strain or chain. Okay, chain of molecule. Okay, and here we have the hydrogen bond. Without this hydrogen bond, this will be one molecule, and this one will be one molecule. But because of this hydrogen bond, okay, we stick these two together. Okay, so you need to change in the number, mass, shape, and electronic structure of the molecule system involved. Okay, so because of this interaction or this hydrogen bond, so the molecule, okay, the molecule can take some other configuration. Okay, so this one again, like in the folding of the protein. Okay, so because of this, some of this hydrogen bond, so the protein will fall to its best position or best configuration. So next is the water. Okay, so again we see that in our body we have a lot of water, and all the molecule will be solute in the water. Okay, so water dominate living process. The behavior of all other molecule in living organism is defined by the nature of their interaction with water. Okay, so maknanya kalau kita ada molekul tu, kita masukkan dalam air, macam mana bentuk dia. Bila kita masukkan dalam alkohol, macam mana bentuk dia. Okay, so we have hydrophilic molecule, so interact easily with water. Hydrophobic molecule do not interact with water, spontaneously form cluster, so minimum contact between hydrocarbon chain and water molecule. Okay, so here we can see that these are water molecule and these are the hydrocarbon. So macam kita masukkan minyak dalam air lah, kan? So all the hydrocarbon will stick together. Okay, so the thermal property of water. So water, so you can see here, molecule weight 18, melting point 0, and boiling point is 100. Uh, Different with other hydrogen based molecule. So the other hydrogen based molecule, the melting point is less than 0, and the boiling point also less than 0. Okay, so why? Because we have this liquid at 0 degree because hydrogen bond. Okay, so the water do the hydrogen bond with other water. So in order to make it the melting point or melt, so we need to cut the hydrogen bond first. Okay, next is the solution sphere shell of water molecule. Okay, so here these are Na plus, Cl plus. Okay, so Na plus the ionic interaction. Okay, so in order to do the ionic interaction, so it must come together first. But because of this water molecule, so the water molecule will make a shield uh, between this Na plus and Cl plus. Okay, so uh, this Na plus and Cl plus need the force to uh, take out or diffuse this water molecule first before they can do the ionic interaction. Okay, steric force. Okay, and here we see that amphiphilic, or nowadays we call it amphipathic molecule. Okay, so containing both hydrophilic and hydrophobic moiety or hydrophobic uh, part. So if we place it in a aqueous environment, so it will produce. So let's say here the uh, the sphere, this sphere show that is a hydrophilic, and this this one is the hydrophobic. Okay, so when we put it in water, so we try hydrophilic part will point out, and hydrophobic part will focus on the center. Again, this one, vesicle, the liposome, and the lemon. So next we have the salt gel transition. Okay, so we know that a gel is a colloidal mixture, which is a type of mixture in which small particles are evenly diffused throughout another substance. So these are example gelatin, or in other case our hair gel. Okay, so these are the gel. Salt is liquid state when change in temperature and therefore molecular motion, metric architecture, and inclusion of solute can lead to a transition. Okay, so here we can see that we have here this if in this temperature it is in crystal, if in this temperature and the water content is high, is in gel. If the temperature is high, okay, so we are going to get, here you can see that lamellar phase, cubic phase, hexagonal phase, and these are colloid. Okay, for the solution. Okay, so we can see here. Okay, this one is just like, let's say we have a gel, so we left the gel in the uh, in the sun or outside, shined by the sun. So we can see that some of the gel changing to uh, just like a water. Okay, so we have this one. Okay, so the last slide, this last slide, The solved phase is optimal, the solution phase. A lipid bilayer integrate with a built-in protein molecule form a biological membrane. Okay, so this lipid barrier or lamella, the built-in protein molecule form a membrane. So we have this the production of membrane. Protein of the membrane can perform various functions such as those of immobilized enzyme, channel, pump, receptor, signal generator, and function of a membrane skeleton. Okay, so these are the some of the function of the protein. Okay, enzyme, channel, pump, and receptor. Okay, so thank you.